Decision trees. This is a diagram, well, a graphical, let's put it that way, a graphical approach to making decisions, as the name implies. There are two items called root nodes and chance nodes. The chance nodes have a probability associated with them. And there is an expected value at each root. And it's not particularly difficult, but let's take a look at an example. It's the best way to illustrate this. Let's say that there is a dice game. And in order to play that game, you have to pay $9. You can, at the root, you can either accept the offer, in which case you pay $9, or you can reject the offer, in which case you pay $0. However, ultimately then, your profit is $0. So you gain nothing, lose nothing by rejecting the offer. And so you think, but you accept it because you think, you know, if I roll a 3, 5, or 4, 5, or 6, and since that's 2 out of 3, I'll get $15. But if I roll a 1 or a 2, that's only one chance out of 3. I don't get anything. I've lost $9. So the probability at this chance node is 2/3 success, 1/3 for failure. Now payment for success is $15, and so the net profit is 6. Here, the payment, if you fail, the payment is nothing, and the net profit is -9. And if you reject the offer, the profit is 0. Okay? Pretty simple scenario. So the expected value then I didn't put the expected values there, but the expected value then is 2/3 times the net profit. Okay, so it's the probability associated with the net profit. Okay, so 2/3 times the net profit is 2 times 6 is 12 over 3, so net profit, the expected value is 4. The expected value of failure is 1/3 times -9, so that's -3. And the expected value of this is 0. Okay? And so the expected value for this node, the expected value here is 0. The expected value for this node then is 4 minus 3, 4 plus -3, or 1. Okay? Which tells me that my expected value is 1 for taking taking this node, accepting the offer, whereas it's 0 for rejecting the offer. And we're going to look at this later, but without any other information about how risk tolerant we are, it would suggest that I should take the chance because the expected value for taking that node is $1, which is greater than 0 for rejecting it. Does that make sense? Right. So that means that my expected value for taking is $1. Now, let's say that it's now a 50-50 chance, $15, and but the chance is half of success, half of failure. So that's 0.5 times 6 is 3. 0.5 times -9 is -4.5. So the expected value of this branch is -4.5. Did I do that right? Let's see. It was 3 and -4.5, -1.5. I'm sorry, that's expected value. Because it's 0.5 times 6 plus 0.5 times -9. So now the expected value of this branch is -1.5 versus the expected value of not playing the game is 0. Now, this tells me that I can expect to lose if I take this chance, so I might as well not. Okay? That's a real simple scenario. Okay?
So what was it, 9 times 6 plus 9?
No, it's a...
okay, that probability.
Yeah, it's probability times 6 plus the probability times -9. That's the expected value for that node. Maybe this. So this node equals 0.5 times 6 plus 0.5 times -9, and then equals -1.5. For the previous example, the expected value is 2/3 times 6 plus 1/3 times -9 equals 1. So first, and also this has, the reason I'm showing you a simple example like that is it has it makes intuitive sense that your chances are better here than in the second scenario. All else being equal, that is. So let's take a look at a more complicated example. Okay. We can produce two things, a pressure sensor or a temperature sensor. The upfront cost for development is, first of all, the probability of success from market is 0.8 and 0.5, respectively. Okay. The upfront cost of development is 10,000 for the pressure sensor, 100,000 for the temperature sensor. The sales revenue, however, with this low probability high cost, or lower probability high cost, is $1 million versus 400,000. Okay. So we have the option of doing the temperature sensor, the pressure sensor, or not doing anything. Expected value being 0. Okay. Let's say we're not doing anything. Temperature sensor development cost is 100,000, and we have a 50-50 chance of succeeding. Okay, if we succeed with our sales revenue of $1 million and $100,000 cost, our net profit is going to be 900,000, and with $100,000 cost, if we fail, we lose 100,000. Expected value is 400,000. Same approach. 0.5 times 900. Plus 0.5 times negative 100,000. For the pressure sensor, 10,000 upfront cost, 80% probability of success, 20% probability of failure, same approach. 0.8 times 390, 0.2 times -10, we have an expected value of 310,000, and in either we have an expected value of $0. This would imply that the riskier outcome, because of the high probability, even though it's not a high probability of success, a high potential profit would allow us to give us a slight edge with expected value and tell us to go the route of the temperature sensor. If the profit were not so high, the outcome would be different, obviously.
What do the little hash marks mean on those two
Oh,
lines?
thanks. The little hash marks means that you've decided not to do those. This is the preferred outcome. I forgot to mention that.
So would this method be biased for higher reward?
Yes. Yes.
So even if you have a very high chance of failure, if the reward is still extremely high.
That's exactly right. That's exactly right. And it doesn't tell you anything about your tolerance for risk. Yeah. So, that's a perfect segue into my next, the next topic here, which is the utility function. What does the utility function look like? Excluding the variable names. It is the cumulative exponential function, where x is time, and r is the mean time between failures. R is the risk tolerance. The only limit on it in this situation is that r has to be greater than 0. Mathematically it doesn't, but it has to be greater than 0 to make logical sense, to make sense in this analysis. So think about this as the mean cost between balking, for lack of a better term, before I say, you know, I'm just not comfortable with spending that much money. You know, with me, I go to Vegas, it's $1 maybe. That's my risk tolerance, and then I'm ready to go. Way too cheap to gamble. And then X is your net profit. Okay? That's your evaluation measure. And then you can use that outcome to calculate an expected utility at each node. Okay? So the expected utility is the probability of the node times the utility function, which we use that. There is something else that's very, very difficult to interpret. It's basically the inverse function, the inverse transform. It's called the certainty equivalent, and what it does is it translates your values back, your expected utility back into monetary units. But I don't want to talk about that too much because I don't think it's as useful as it's touted to be. So we'll stick with the utility function. Yeah.
On the previous slide, you said the mean time between a failure. Balking. Okay. And what value is that? Is that going to be your minus?
It's always that's going to be the R.
It's going to be the R. Okay.
Yeah. And X is the net profit. Okay. Here's one that I pulled out of my Kirkwood. Actually it's online, and it's a pretty good primer on decision trees. And I pulled this out of there. It's kind of business oriented, but this guy's a professor of, I think, operations research in the business school down at ASU. And but it's pretty good. It's online. It's free. So if any of you want it, I think I have it somewhere. I can put it up on the blackboard. So here we have cost associated with either waiting or not waiting or not purchasing an export license, or an import license, sorry. Same difference. So here we purchase it, costs us $5. We don't purchase it, costs us $0. Or we wait, it costs us $0 right now, and then we issue the import license. The import license is issued. Here we wait to see whether or not it's issued, and if it's still available after it's been issued, because here we buy it up front, whether it's been issued or not. Here we wait to see whether it's been issued, and then pay for it afterwards. And so this is a more conservative approach, is to wait to see whether it's possible to get it. That's probably a better way to put that. Is it possible to get an import license? Here we pay for it up front, and if we get it, we immediately have it. Here we wait to see whether it's available, and or whether it's being issued, and then whether or not we can get it. Okay, because that's the risk of waiting. Because if you wait until it's been issued, then you only have a 30% probability of being able to get one. That's the disadvantage of waiting. The advantage of it is the disadvantage is paying money up front, but then when it's issued, you have it. You're certain to have it. There's only a 50-50 chance of it being issued. Okay. So does the scenario make sense? Okay. So we have these three alternatives. Don't do anything, buy it now, wait to buy it later. Here, if we are assuming a risk tolerance of 2 million, I have it in 2, everything's in millions, okay? So we have it in 2 million, and we have the net profit through here. We get 8 million revenue, we spent 5 million up front, we have a net profit of 3 million. We spent 5 million up front, it wasn't issued, we just, we still, for some reason, there's still some revenue to be gained. And I can't remember, there's still capability of gaining revenue for it, but it's still, you still lose $1 million in this scenario. Here, you have 0.5 for probability, and you haven't spent anything yet, so then at 0.3 probability, you get it, then you spend your 5 million, you make 8 million, you have a $3 million profit. That looks like it's a pretty good option because the profit is still the same. The advantage of it is that if it's not issued or if it's not available to you, you don't lose anything. Whereas up here, if it's not available, you do lose something. Now let's say that your mean time between balking, your R, is $2 million. That you say, yeah, once I get to $2 million, I'm not willing to take any more chances. And you arrive at that from just your past behavior. Okay. So, the expected value at this chance node then is $2 million. 0.5 times 3 times 0.5 times -1 is 3, and -1, that's 2. The expected value here obviously is 0. The expected value here is, and what did I do with my expected value? Anyway, the expected value here is is 0.3 times 3 and 0.7 times 0. So 0.3 times 3 is 900,000. 3 times 3 is 900.9. Yeah, $900,000. So the expected value here is 900,000. That's less than there. However, my utility function tells me that in this case it is the utility of x4 is 1 minus e to the minus 3 over 2, and that equals 0.777. Here, you call it u to the x1, or call it u to the x2 is 1 minus e to the minus -1 over 2, and equals -0.649. So that has negative utility, obviously. This has 0 utility associated with it. This one, I'll call that u of x2, is pretty much the same. 1 minus e to the minus, because it's $3 million net profit there, 3 over 2 equals 0.777, and u of x 1, let's see, call that 3 and 4, sorry. 1 minus e to the minus 3 over 0, and that equals 0. Okay? So, then I go back here and I take my expected utility is expected utility here is 0.5 times so 0.5 times 2.33, That's what it is, 0.5 times 2.33 and 0.5 times 0. So it's basically 0.5 times 2.33, and that's where we get 0.117. Okay. So this node right here, it has an the best expected utility is 0.117 because that has a better utility given my risk tolerance than does this chance, which is has a chance of just as much profit, but I have more likelihood of getting 0 here, but I have absolutely no likelihood of losing anything, and the same profit. So I would be better off waiting, even though I have only 30% chance of actually getting my input, according to this decision. Does this make sense? Now, I thought it would be interesting to take a look at how your trading decision, your expected utility changes as your risk tolerance increases from 1 million to 10 million. Okay. This is for option 1. And option 2 is better, but as your risk tolerance increases, then suddenly option 1 becomes better. And so you can see that it evolves as your risk tolerance increases, and it will change your decision based on your risk tolerance. For the dice game, I know this is small, but I just wanted to remind you, where there's 2/3, 1/3 versus 1/2, 1/2, otherwise the same. This is what the expected utility. And let's see, since this is in dollars, I had the expected utility go from $10 to $100, $1,000. And so here on this increment, you can see that it's pretty consistent that this one is going to be preferable all the way up to $1,000 when it kind of converges. So it changes substantially based on this one will always be greater utility than that one. That's essentially what I'm saying. But I just thought that would be interesting to illustrate that. Okay. Let me start and introduce Markov, because like I said, I don't think we really want to get into it at this point. It is, I won't say it's complicated, but there are many steps associated with it to keep straight, so let's put it that way. But let's introduce it anyway. So we can get the idea. This is where you have probabilistic probabilities. That's what stochastic conditions are. So it means that there's a probability associated with different conditions. And you have a number of finite states. It's not infinite. There's a number of finite states of the system. And just like in simulation, we have the African tanker problem. In Markovian decision processes, we have the Gardner's problem. A little bit more mundane, but nevertheless, that's what they call it, the Gardner's problem, because it's easy to think about. First thing we want to define, and this is important to understand, is we have a transition from 1 year to the next year. And we have 3 states. This is called the transition matrix. The state of the system is good if it's called 1, fair 2, and poor 3. So the way you read this is, if in this year the state of the garden, or the state of the system, is good, the probability that it will be good next year is 20%. The probability that it will be fair next year is 50%, and the probability that it will be poor next year is 30%. These rows have to add up to 1, okay? Because it has to be 1, 2, or 3, so it's evenly divided between 1, 2, and 3. If it is currently fair, next year it can't improve, so it's a 0 probability that it will go to good. It's a 50% probability that it will stay fair, and there's a 50% probability that it will become poor. Since there's no opportunity for improvement, if the state, the system is currently in a poor state, it can improve to 1 or 2, so there's a probability, it's deterministic that it will be poor next year. It will stay that way. Okay. So, like I said, this is called, in Markovian parlance, this is called the transition matrix. And you usually designate it with a P, superscript 1. I know it should be T because it's transition, but it has probabilities in it, so that's why it's a P, a capital P, with a superscript 1. Because we can't have more than one possible transition matrix for a system. We're going to talk about that. An interesting way to represent this, that's often used, these can get quite complicated, is what's called a Markov chain. And it's a graphical depiction of this transition matrix. So if you're in 1, you remain in 1 with a 20% probability. You move to 2 with a 50% probability, and you go to 3 with a 0.3% probability. If you're in 2, you have 0% improving, 0.5% of remaining the same, and 0.5% of degrading. If you're in 3, you can't go to 2, you can't go to 1, but with a probability of 1 you remain in 3. This graphical representation is often used for the transition matrix. I won't be talking about it too much because I don't think it's going to help us overly much, but I think that it's a good idea to be aware that a Markov transition matrix is often represented as, like I said, what's called a Markov chain, graphical representation. Okay. The return matrix, which thankfully is called R. The return matrix, again, this is kind of like the game theory. The return matrix, you have to know what the benefit or the cost is associated with each transition. Okay, so if we're going, the cost associated with starting at 1 and remaining at 1 is 7. The cost associated with starting at 1 and degrading to 2 is 6, and so on. Okay, so these return matrices are the costs associated with this transition matrix. If we have another transition matrix, okay, this is a second transition matrix where it is possible to improve, and we have costs then associated with improvement. Okay? So this is the return matrix that is associated with this transition matrix, and this is the return matrix that's associated with this transition matrix. Then the next step is to define your policies. Okay? With a relatively small system like this, it's possible to define them by enumeration. And what we're going to do is to, since this is a gardener's problem, under what conditions will we fertilize? Will we apply fertilizer to our garden? Because it has a cost associated with it. Stationary policy 1 is to never fertilize. Stationary policy 2 is to always fertilize. Those are the two extremes. 3, the rest of them are more specific. 3 is to fertilize when in state 1. 4 is to fertilize when in state 2. 5 is to fertilize when in state 3. And then all the combinations. When in 1 or 2 fertilize, when in 1 or 3 fertilize, when in 2 or 3 fertilize. They don't necessarily all make sense, but they are all the possible policies that we could implement. Okay? Oh, and by the way, the other thing that I forgot to mention, this is the return matrix for this is the return matrix for never fertilizing, and this is the return matrix for, or the transition matrix for always fertilizing. Never fertilizing makes sense. You never put anything into it, it's never going to improve. But it might stay the same if you're lucky. Whereas here, there is a possibility for improvement if you apply fertilizer. So you have a transition and a return matrix for doing nothing, a transition and a return matrix for always doing something, for always fertilizing. Each of these policies represents a rearrangement of those two matrices. Right? This policy is just a net return. Always fertilizing is just this transition and net return. All the other 6 have a rearrangement associated with them. Let's talk about the rearrangement a little bit. So let's assume that we're going to result. So let's say that we are going to apply fertilizer only in state 1 when soil conditions are good. So that means that when the current state is 1, I use the transition matrix, which is associated with fertilizing, and the return matrix, which is associated with fertilizing, and I use the transition matrix rows 2 and 3, return matrix rows 2 and 3 that are associated with not fertilizing. Okay? So the point 3, point 6, and point 1 come from here, as do the 6, 5, and negative 1. And the other 2 rows come from here. Right? Does everybody see the rationale here? Does it make sense? Okay. There's a value associated with each policy. This is value with policy with probability of return matrix 2, superscript 2, and for condition 1, for state 1, value associated with probability of return matrices for 1 associated with state 2 and 1 associated with state 3. The way we get these values is to just take 0.3 times 6, 0.6 times 5, and 0.1 times negative 1. So that 4.7 is, no, I think that how we're doing that. 0.3 times 6 plus 0.6 times 5 plus 0.1 times negative 1. And that equals 4.7. So that's 1.8, 3, and negative 0.1. So that's 4.8 and 4.7. And just to illustrate the other ones, that's V, 2, 1, sorry. V1, 2 is 0 times 0, and 0.5 times 5 plus 0.5 times 1. And that's 2.5 and 0.5, that's 3. And that's 3. Get the idea? So those are the values associated with each of the current states, good, fair, and poor, given that particular policy, which is to fertilize when it's currently in state 1, and if it's, in other words, if it's good, if the garden is currently good, fertilize it. If it's fair or poor, don't bother with it, essentially is what this policy is. And that's the values associated with each one of those actions. Now, let's say that we say, okay, if it's good, that means that it doesn't need to be fertilized, and if it's fair or poor, then we need to put fertilizer on it. So now, it's the don't fertilize the first row for the transition and return matrices, and fertilize for 2 and 3 for the transition and return matrices there. Our values here are those. I calculate them in exactly the same way. Again, notice the notation here. It's V sub k, where k is the, or V to the k, where k is the, refers to the transition and return matrices, which here are to fertilize. We just arbitrarily called it 2, doesn't matter, it's just identification for policy 1. This is V to the first, which is the don't fertilize, and we arbitrarily called that 1 for state 2, and V to the first for state 3. And so K is the transition matrix, the original transition matrix to refer to, and I is the current state, or for the state. Okay? Same way here. It's V to the first sub 1, V to the second sub 2, V to the second sub 2, because here we used, for fair and poor, we used transition and return matrices 2, and for 1, we used a transition and return matrix 1, the current state. Okay. I think that's enough for today. I think that, think about that. I'll briefly review this next week. And then we'll go on and do the dynamic and some of the programming techniques, the more cognitive decision. Any other questions?
I do.
Okay.
So back on 41, slide 41, you said never fertilize was P1 up top, always fertilize. Is that a set thing, or is that we just chose those two?
They're arbitrary choices. Okay. We could have called it the other way if we wanted to.
Okay, yeah, because then on the next slide where you start off one on the good, and then you apply the second and third row.
Yeah. So this is still never fertilize, always fertilize, but that's an arbitrary.
Okay. Yeah, I was just wondering if those two, because then you have here starting with 0.3.
Well, that's because this is a specific policy of
applying the conditions are good.
never fertilizing.
Yeah.
That's what this if conditions are good, but then or always fertilizing if it's good, and never fertilizing if it's fair or poor. And we don't give that a superscript designation. It's just whatever our current proposed policy is. Does that help? Anything else? Okay, thanks. I'll see you next week then.